These are 5 short presentations on common and widespread misunderstandings on quantum mechanics. The first presentation is on the so-called collapse of the wave function. The second presentation is on the so-called measurement problem. The third presentation is on the misunderstood link between quantum entanglement and Bell's theorem. The fourth presentation is on the so-called EPR paradox, and the last presentation is on the so-called incompleteness of quantum mechanics. Each talk is accompanied by a brief description and the necessary and relevant references. The idea for these talks has already been published in Fundamentals of Quantum Entanglement, second edition, published in 2022 by the Institute of Physics in the UK. Organic lasers and organic photonics, published in 2024 by the Institute of Physics, and Quantum Optics for Engineers, Quantum Entanglement, published in 2024 by Tyler and Francis. So now we proceed to our first presentation. The collapse of the wave function in quantum mechanics, unnecessary. The collapse of the wave function is a conceptual tool often used by critics of quantum mechanics, mainly non-quantum theoreticians. However, the collapse of the wave function is an unnecessary concept that has no impact whatsoever on the quantum measurement. According to Freeman Dyson, quantum mechanics is composed of 2 layers. The first layer is the mathematical layer of imaginary numbers, complex numbers, wave functions, and probability amplitudes. The wave functions and the probability amplitudes are synonymous. The second layer is the measurable. So that's unobservable. The second layer is the measurable. And that includes quantum probabilities, quantum polarizations, and quantum intensities. Quantum intensity is directly proportional to the quantum probability. These 2 layers are linked by Born's rule, and we will describe that in more detail as we proceed. The collapse of the wave function was a non-physical concept introduced by Heisenberg in 1927, and it was taken up by John von Neumann in his book The Mathematical Foundations of Quantum Mechanics in 1932. It should be mentioned that neither Dirac nor Feynman, in their iconic books The Principles of Quantum Mechanics and the Feynman Lectures of Physics, 3rd volume, mention or refer to the collapse of the wave function. Feynman, in his Lectures on Physics, says that interference is at the heart of quantum mechanics. So let us consider n-slit interference, where we have either 2 slits or 2000 slits, and the interferometric plane that could be composed of a photographic plate or a CCD detector or a CMOS detector. It is the probability amplitude that must correctly describe the physics in all its parameters: number of slits, wavelengths, geometrical configuration. This probability amplitude, then multiplied by its complex conjugate, gives us the probability. So probability amplitude, complex conjugate of the probability amplitude provide the probability via Born's rule. We will refer to the Born rule toward the end of this little presentation. If there were an hypothetical collapse of the wave function in the interferometric situation, that would mean that the superposition probability amplitude of either 2 slits or 2000 slits would have to reduce to a single state. That would occur in the first layer of quantum mechanics, which is the unobservable layer, and it would add nothing to the measurement, no further information whatsoever. It would be a completely parasitic step. And we know that nature is wonderfully efficient. It doesn't do anything that is unnecessary. Let us here cut a little bit of a slack to John von Neumann, because John von Neumann didn't know about the non-locality of the photon in 1932. And an hypothetical collapse of the wave function also is contrary to the observed non-locality of the photon, which is an experimental fact. And that is described in detail in Fundamentals of Quantum Entanglement, 2nd edition. As far as quantum entanglement is concerned, we have a probability amplitude of either two photons, 4 photons, 8, 16, 32, multiplied by the corresponding complex conjugate, and then we are provided by the probability, which is the measurable. A collapse, again, would introduce an unnecessary intermediate step. So, in conclusion, the collapse of the wave function is unnecessary, it would be unobserved, and it is non-existent. Now, early in the presentation, we did refer to Born's rule. When Born introduced his rule in 1926, he did so completely out of the blue. He never derived it, or he never provided proof for it. If you would like to see a transparent, direct interferometric derivation of Born's rule, refer to chapter 16 in organic lasers and organic photonics. Our next presentation will be on the so-called measurement problem.